So we talked earlier about this idea that the Bohr model has orbits, but the quantum model has something called orbitals. So these are orbitals. They have different shapes, which account for the probability of the wave functions in different spaces. So the basic ones are what are called s and p orbitals. S orbitals are simple, and they are just a sphere. You can see here a sphere. The darker circles are just like the 2s and the 1s. So we go from lowest energy. Remember, so these numbers here are the n values that we saw earlier. So remember, we saw the ground state was n is equal to 1, first excited state is n is equal to 2, and so on. So the solutions to the Schrodinger equation yields the probability in 3 dimensions for the likelihood of finding an electron about the nucleus. So depending on the equation for which orbital it is referring to, we have different spatial orientations or spatial probabilities of finding an electron. It is these probability functions that give rise to the familiar hydrogen-like orbitals that electrons occupy. So usually whenever we draw out s orbitals, we have spheres, and p orbitals, we have dumbbells or bow ties or whatever you want to call them. So we can see here for the 2p, we have, one node. We have 2 spheres basically beside each other with the node in the middle. Let's see if I can draw a different color. So we have a node here down the middle where there's a gap. So they kind of like, think of like 2 like tennis balls or something where they, you can put the 2 tennis balls together. There's a point where they touch. Imagine the point where they touch is an infinitesimally small gap, and then that would be the node. The shape of the p orbitals is more or less small spheres, and they're kind of like squished spheres, so they're not perfectly spherical, but it's close enough for the purposes of what we're going to be doing. So so we've got these sort of shapes. They're orientated on a Cartesian axis, so this x, y, z. Of course, an atom doesn't actually align itself with Cartesian axes. We just do it arbitrarily for our ease of understanding as human beings. We have s orbitals, we have 1 of in each shell, which is these n values. And then the p orbitals, we have 3 of those, but we'll see how we can know that later on with quantum numbers and so on. We have 3. They orientate themselves orthogonally to each other, so that means that they're 90 degrees to each other. So the px is pointing along the x-axis here, x-axis. Py is pointing along the y-axis here. Pz is pointing along the z-axis, up and down. Okay. So yeah, so the quantum numbers then allow us to just sort of identify or give an address to a particular electron. So the quantum numbers and electron orbitals, quantum numbers are terms that arise from the mathematics of the Schrodinger equation. They describe location of an electron in a particular orbital, much like an address does. Each electron in an orbital has its own set of 3 quantum numbers. So we have the principal quantum number where n is equal to 1, 2, 3, 4 up to the infinity shell. And we have the azimuthal or angular quantum number where L is equal to 0, 1, 2, 3 up to a maximum of n minus 1. So this is a subshell. And then we have a magnetic quantum number, ML. ML may take any value, take on the value of an integer from minus L to plus L. These are the individual orbitals. So we have 3 principal quantum numbers right now. We'll add a 4th later, but for now we have 3. We have the n, which is the principal quantum number. So that's like our ground state is n is equal to 1. Our first excited state is n is equal to 2, and so on up to infinity. Infinity is the point at which we ionize the electron. Azimuthal or angular quantum number, so L, then this defines the subshell, so it can have values of n minus 1. And magnetic quantum number, ML. ML may take on the value, an integer from minus L to plus L. These are the individual orbitals. So let's go back here a wee minute and have a look. So here n is equal to 1 at the bottom. So n is equal to 1. So that means that L is going to be equal to, the values L can take, are going to be from 0 up to n minus 1. So n minus 1 is 0. So here we only have 0, which means we only have one type of orbital available in the ground state at the n is equal to 1 state. So, or n is equal to 1 shell. So this means that we end up with this idea that ml can take values from minus L to plus L. So that means we're going to have only values of 0 available, because plus 0 and minus 0 are still 0. And so this tells us that there can only actually be one orbital at the n is equal to 1 quantum number, principal quantum number. So in this shell, n is equal to 1, we can only have one orbital here, which is the 1s orbital. If we then go to the n is equal to 2 level, we have more opportunities. Let me just get rid of this. Okay, and then, all right, so n is equal to 2 for this principal quantum number level. So there's 2's here. You can see those 2's. That's what this number at the front means. It's the principal quantum number. So n is equal to 2, or shell of that particular quantum number. So L can then take values up to n minus 1. So L is going to be equal to 0 and 1. So it can take values from 0 up to n minus 1. So n minus 1, 2 minus 1 is 1. So these are the values 0 and 1. So that means we could have 2 types of orbitals. And that's in fact what we do have. We have the s orbital here, the spherical one, and we have this bow tie shaped one, the p orbitals. Then, so if L is equal to 0, ml for L is equal to 0 is going to be equal to 0 again. So we only have one s-type orbital. That's the same as here. But then if L is equal to 1, ml can now be equal to minus L to plus L, going through 0. So that means we could have minus 1, 0, and plus 1. And so that's, if we can count them together, we have 1, 2, 3 individual orbitals. We have 1, 2, 3 p orbitals. So L is equal to 1 is the p orbitals. We'll talk more in detail about that shortly. But basically, this is the way that we can determine how many of each type of orbital there is. Eventually, you'll just kind of remember that there's one s orbital, there are 3 p orbitals. Especially when we do electron counting, that'll become even more obvious. Okay, so here we have it written out. This is kind of a summary of what I was saying. So n defines the principal energy level or shell. So these are, there are n subshells for each n level corresponding to L. So if n equals 1, then we can have L values of 0. If n is equal to 2, then we can have L values of 0 and 1. And if n is equal to 3, then we can have L values of 0, 1, and 2. So here the maximum L can be is n minus 1, so that's 0. Here as well, maximum is n minus 1, so that's 0 and 1. And here as well, n minus 1 is the maximum. N is 3, so the maximum will be 2. So then for each L value, we have 2L plus 1 ml numbers or orbitals. And these are separated by orientation. So they are usually orientated so that we can have a minimum of contact between them. So we saw that with the p orbitals here, where they're pointing along orthogonal axes. So they're pointing at 90 degrees to each other, which means that they will have the minimum possible energy while still being orientated around the nucleus. The nucleus is taken as sort of like the 0, 0, 0 point on the XYZ axis. So each L is divided into 2L plus 1 ml orbitals separated by orientation. So if L is equal to 0, L is equal to 1, or L is equal to 2, we can have different ml values. So L is equal to 0, ml can be 0 because, or can only have one value. So if L is equal to 0, so that's 2L plus 1. So 2 times 0 is 0, plus 1 is 1. So the only value you can have is 0. And this is true because this is the s orbital that we saw earlier. There only is one s orbital. When L is equal to 1, we have 3 possible orbitals. So 3 here. So we have 1 here, 3 here, 0, minus 1, and plus 1. When L is equal to 2, ml is equal to 0, plus or minus 1, plus or minus 2. We have 5 orbitals here. That's 2L. 2 times 2 is 4, plus 1 is 5. Okay. So quantum numbers on electron orbitals. So each L within an n level represents a subshell. Each L subshell is divided into ML degenerate orbitals, where ML designates the spatial orientation of each orbital. Okay. So the type of orbital here, so L is equal to 0, S subshell is sharp, so the number of orbitals is 1. L is equal to 1, the P subshell, principal, so it has a number of orbitals here is 3. L is equal to 2, this is the D subshell, so diffuse, the number of orbitals is 5. And L is equal to 3, the F subshell, fine, number of orbitals is 7. So each L within an N level represents a subshell. And each L subshell is divided into ML degenerate orbitals, where ML designates the spatial orientation of each orbital. So we have letters that we can assign to these. So when L is equal to 0, this is the S subshell or S type orbital. And they also have like these sharp, principal, diffuse, and fine. Those are not really used much. It's usually just S, P, D, and F. And for our purposes, we'll only really be dealing with S and P orbitals, but D orbitals can come up and F orbitals very rarely. But just make sure that you know that 0, L is equal to 0 corresponds to S, L is equal to 1 corresponds to P, L is equal to 2 corresponds to D, and L is equal to 3 corresponds to F, and then the number of orbitals in each of those. But remember that the number of orbitals is easily calculated as just 2L plus 1. So this quote from Ernest Rutherford, as he described the mental leap on going from classical to wave mechanics or quantum mechanics. So I was brought up to look at the atom as a nice hard fellow, red or gray in color according to taste. In order to explain the facts, however, the atom cannot be regarded as a sphere of matter, but rather as a sort of wave motion of a peculiar kind. The theory of wave, quantum mechanics, however bizarre it may appear, and it is so in some respects, has the astonishing virtue that it works and works in detail, so that it is now possible to understand and explain things which looked almost impossible in earlier days. So here he's talking about the great leap forward that was made when wave or quantum mechanics was postulated and formulated together. Things that they could not explain previously. There's a lot of like phenomena that they observed, but they couldn't quite understand or rationalize with experiment based on classical behaviors. You know, things like this quantization of energy. That is something that doesn't make any sense whenever we think about macroscopic materials. Think about if you've ever been in a car or public transport or whatever. Thankfully, the car or public transport doesn't jerk forward as it changes its energy level. So it goes from 0 kilometers per hour to like suddenly 10 kilometers per hour. It can't go from 0, 1, 2, 3, 4, 5. It goes 0 to 10, so it's a jerk. And then it changes gear, it goes to 20 and 30. And so every time you're jerking forward, whenever it changes its energy or speed. Thankfully, that's not the case. So orbitals are the region in which an electron can be found within an atom. And so this is the sort of probability of finding that electron. And remember, it can be defined as the wave function squared. Orbitals and quantum numbers then, so different orbitals have different quantum numbers. Think of the quantum numbers as kind of an address. Orbitals have characteristic size and shape. So S orbitals are generally spherical. P orbitals are dumbbell shaped. Those are the only two shapes you really need to remember for this class. N is the principal quantum number, energy and size. L is the angular momentum or azimuthal quantum number. So generally you'll find angular momentum is the more common name now, but in classical texts, you'll see azimuthal quantum number a lot. ML is the magnetic quantum number, so that's orientation. And orbitals with the same N are in the same shell. So this is the shell. This is sort of the subshell or type of, or orbital type. And then this is the actual orbital it's in, or the orientation of the orbital it's in. Okay. So orbitals with the same N and L are in the same subshell, so I've just written that out here. And then ML is sort of the orientation of that subshell. So quantum number summary. So NL, ML describe an orbital, like the direction that it's facing, its shape, and its sort of energy. So its energy comes from this N value, this shell. L gives the type of orbital or the shape, and ML gives its orientation. MS then is the fourth quantum number that I talked about. It describes something called the spin of an electron in an orbital. And so this is something that comes about in the mathematics of the wave function as a requirement for obeying certain phenomenological laws associated with quantum mechanics. So they have a spin, it's usually either up or down. It's either plus or minus a half is the number given to it. 1 over 2. So a set of 4 quantum numbers then describes an electron. So for example, if the N quantum number is the country you live in, L is then, so for example, this is the country, so the Philippines. L could then be the city, like Quezon City. L could then be like the street, Katipunan Avenue, and then MS could then be like the building inside the university. You even get more. You could go MS could be the office or the lecture theater, then ML could be the building, L could be the university, and N could be the city. So no 2 electrons in an atom can have identical sets of 4 quantum numbers. This is the Pauli exclusion principle. So one of the ways that it can be formulated is to say that no 2 electrons can have the same set of 4 quantum numbers. So that means that 1 electron in an orbital, so each orbital can hold 2 electrons. And inside that orbital, one must be spin up and one must be spin down, or one must have MS of plus a half and one must have MS of minus a half. But since like the MS values are not included in this figure or this table because it's not, it doesn't really change like based on N or L or ML. They can only have one of 2 values, and it doesn't matter which orbital you're in. MS is either plus a half or minus a half. So the principal quantum number has a symbol of N, as we've seen. So it has values 1, 2, 3, 4 up to infinity. So when then we have the angular momentum quantum number, so it has a symbol of L, so it can take values up to N minus 1. And then ML, it can take values from minus L to plus L. So L is dependent on N, and ML is dependent on L. So N is the only sort of independent quantum number. So in the N is equal to 1 level, that's the 1s. We have only got one type of orbital, which is this 0. So it's an s orbital. Then we can only have one s orbital. So we have one s orbital in the N is equal to 1 level. At the N is equal to 2, we now have 2 types of orbitals. We have s and we have p. And then N is equal to 3, we have 3 types of orbitals. We have S, P, and D. And then we have, for the principal quantum number 4, we have 4 types of orbitals. We have 0, 1, 2, and 3. So that's S, P, D, and F. And so we'll have different total numbers of orbitals possible in each one of these principal quantum numbers or shells. So we have a 1s orbital here. So it's 1 orbital in the N is equal to 1 level. In the N is equal to 2 level, we'll have 4 orbitals because we have 1 s orbital and 3 p orbitals. In the N is equal to 3 level, we have 9 orbitals. So we have 1 s orbital, 3 p orbitals, and 5 d orbitals. And then for the N is equal to 4 level, we have 16 orbitals because we have the 9, which are the same as the N is equal to 3, plus an additional 7 f orbitals. So we have 16 in total, 4 types, and N is equal to 4 shell. Yes, Andrew?
Also, I think I would like to note, I just found this as an observation, but as the N value increases, the total number of orbitals and their types are all the squared values of the N values.
Yes, but that only works up to N is equal to 4. Once you get to N is equal to 5, F orbitals are the maximum type of orbital. There is no orbital beyond the F orbital. So even when N is equal to 5, so this work, yeah, that works for the first 4, the squaring, but then after that, it doesn't work. Because we don't create any new orbitals at N is equal to 5. But yeah, you're right. For these 4, it is the square. But then at N is equal to 5, it's no longer the case. because there is no orbital beyond the f orbital. Okay. All right. Thank you for that observation. It's very accurate. So that'll do us for today. I realize that I'm kind of using up a lot of time. We'll continue on Friday. Thank you. Good morning, everyone, and welcome back to the next lecture we have in this series. I don't know how long my battery is going to last. My building is fixing the electricity. They were supposed to do this at 3 p.m. They have decided to do it now, which is not great. So I'm using my phone internet. So if my internet connection is not great, it's probably because of that. So I apologize in advance. I also don't know how long my laptop battery will last. It's got a lot of charge at the minute, but anyway, if I suddenly disconnect, you know why. Anyway, I'll try and come back. I have a backup device that I can use if ever, but let's get started and see how far we can get. So last time we were talking about quantum numbers. We were sort of talking about this idea that there are 4 quantum numbers, 3 which can change significantly, and then there's the last one which doesn't change so much. So there's the principal quantum number. This is kind of like the shell of the electron. So like there's different shells. There's like inner shells which are closer to the nucleus, and then as we go further and further away, there are outer shells. They change in energy as the number n increases, then the energy also increases. These are just kind of like telling us which shell the orbital will exist in. And then there's L, which is more to do with the shape of the orbital. So we encountered the fact that the maximum value for L is based on n. So whenever n is 1, the maximum value for L is 0 because the maximum value is n minus 1. Now, what this means is that in the n is equal to 1 shell, there can only be one type of orbital. This L is equal to 0. And then as we increase the values of n, we get more values of L, which allow us to have different shapes of orbitals. We had s orbitals, which were spherical. We had p orbitals, which were kind of like a bow tie or dumbbell shaped. And then we had d and f orbitals, which we didn't quite go into in detail as to their shape, just that they were called d and f orbitals. Then there's also the magnetic quantum number, this ml, which gives the orientation or direction that the orbital points in. Now, the L is equal to 0, so the s orbitals, they only have one orientation, which is 0, and that kind of makes sense. If you think about a ball or a sphere, how can you tell which direction the ball or sphere is pointing? It's uniform across its surface. Whereas if you think about the p orbitals, they have a bow tie shape. You can tell which direction that's pointing in. That's kind of like the bow tie shape. So it could be pointing that way, it could be pointing up, down, whatever. Usually we talk about these orientations in terms of the x, y, z axes. So the available values of ml are going to be from minus L through 0 to plus L. So whenever L is equal to 1, we have minus L, 0, and plus 1. Okay. Then in the case of n is equal to 3, we have angular momentum quantum numbers of 0. We also have it of 1 and 2. So the ml value for L is equal to 2 goes from minus 2, minus 1, 0, plus 1, and plus 2. So the number of L or ml values, sorry, is 2L plus 1. So L is 2. So 2 times 2 is 4, plus 1 is 5. And that indeed gives us the 5 ml quantum numbers found here. Here's just a little summary of it here. And then the last quantum number is the ms quantum number. This can either be this is the spin quantum number. This can either be pointing up or pointing down, either plus a half or minus a half. So allowed quantum numbers. So n can go from 1 to infinity, 1, 2, 3, 4. As the numbers increase, the energy distance between them decreases. So they start to converge towards infinity. Then L can have values from 0, 1, 2, up to n minus 1, but in reality, we only really have these 4 types of orbitals. It's S, P, D, and F. Even though we can have higher values of n, we only really have these orbitals here. Then ML values can go from minus L to plus L. So there's like, the total number of ML values will be 2L plus 1. Okay. And here is some of the shapes. So I asked you before to sort of be familiar with the s orbitals and the p orbitals. So s orbitals are spheres or circles, and if you're drawing it in 2 dimensions, and then we have the dumbbell shaped p orbitals. Really, it's more like, I draw it very well, something like this. Kind of like 2 spheres. If you imagine 2 like beach balls or something pushed together, whenever they push together, where they meet, it kind of becomes flatter. So that's kind of where the node is. So those are p orbitals. So d orbitals, they have different shapes. Don't really need to remember those for this class, but just sort of be familiar that all of the different letters, S, P, D, and even to F orbitals, they just have different shapes. Just be aware of that. So s orbitals then, we have here sort of like the projection of where the electrons can be within a sphere of radius r. This r will give, so you can see these little kind of gray dots, hopefully. I'm not sure how well you can see that, but they're like little gray dots. And so that's kind of locations at which electrons have been found or electrons could be. Just sort of giving you a probability. You can see it's kind of darker towards the center, and then as we go further out, it's there are fewer and fewer dots. And so this can be represented here in a graphical form, where we have the probability of finding the electron at a given distance from the nucleus versus the distance from the nucleus. And you can see that initially it's quite low because the available space is limited, and then as we get closer to the max, we have a maximum here, which is reasonably close to the nucleus, but not so not too far away. And so the most probable distance of the hydrogen 1s electron from the nucleus is going to be 52.9 picometers. So you can see here it rises to a maximum and then decreases down as we go towards infinity. So eventually we get to a point where the electron is no longer found near the nucleus. You know, it is attracted to the nucleus. So L is equal to 0, ML is equal to 0. We have 2L plus 1 is equal to 1. So that means that there only is one type of orbital. It makes sense. There's only one orientation for a sphere, and that is not really any orientation. So one s orbital that extends in a radial manner from the nucleus, forming a spherical shape. So this darker patch near the center corresponds to this kind of function here, where we can see that there is a maximum which is swiftly reached, and then over time there's a decay where we see that there is a limited chance of finding that electron. P orbitals then, so this is this idea of like the sort of 2 beach balls squished together. They're kind of 2 spheres either side of the axis, which is where the node is, but they're not exactly spheres. They're kind of squished up a little bit. So these have nodal planes. So we see is that the nodal plane, there's always at least one node in a p orbital, and then this node, conveniently, because of the way that we have orientated it, the node lies directly in the middle of the orbital. So something like those should have the same size, but yeah. Sorry about that. So the node is something like there, where that blue line is. And so if we orientate it correctly, so for example, if we orientate the orbital along the x-axis, so x here, then this node here is going to be along the y and the z axes. So here we can see the px has a node in the YZ nodal plane, the PY has in the XZ nodal plane, and the PZ has in the XY nodal plane. Basically, these orbitals are PX, PY, PZ because they point along the Cartesian axis. So one points along the x-axis, one points along the y-axis, sorry, and one points along the z-axis. Then the nodal plane, the point where the probability of finding the electron is 0, that is perpendicular to that orbital. So the facing of this orbital is PZ, so the node will be perpendicular to that, which is then the XY nodal plane. So it's in the XY plane. So it's quite easy to remember. Well, there is a trick to remembering it anyway. So if it's PX, then the nodal plane is the other two members of the Cartesian axis, Y and Z. If it's PY, then PY is the facing or direction of the orbital. And so X and Z is going to be the nodal plane. And then whenever the nodal plane or whenever the orbital points in the PZ direction, then the XY is going to be the nodal plane. So you always have X, Y, and Z as your Cartesian axes. So if we have Z as our orbital, then XY is where the plane will be. So just a wee thing to remember. So the three degenerate p orbitals spread out on the x, y, z axis 90 degrees apart in space. Degenerate just means that they have the same energy. I think we encountered that before, but just to remind you, degenerate means the orbitals have the same energy. So d orbitals, so s orbitals have no nodal planes, L is equal to 0. P orbitals have one nodal plane where L is equal to 1. And d orbitals therefore have two nodal planes where L is equal to 2. So as we change the L value, it also corresponds to the number of nodes which are present. S orbitals have no nodal planes, L is equal to 1. P orbitals have one nodal plane where L is equal to 1. And d orbitals have L is equal to 2, and so have two nodal planes, at least in their first instance. And so that's just sort of L corresponds to number of nodal planes. So the arrangement of electrons in atoms. So each orbital can accommodate no more than 2 electrons. And this is because no 2 electrons can have the same set of quantum numbers. So remember, we have 4 quantum numbers. We have N, we have L, we have ML, and we have MS. So no 2 electrons can have exactly the same orbital, set of quantum numbers, and this is also called the Pauli exclusion principle. So say we have a bunch of like the p orbitals here, we could fill in electrons such as this. So this could be, say this is n is equal to 2. So L here is equal to 1 for all 3 orbitals. ML then is going to be equal to -1, 0, and +1. We can check that because L is equal to 1, so that's going to be 2 times 1 plus 1 is going to be equal to 3. So our -1, we have 0, and we have +1 here. Okay. Then that's 3 quantum numbers, N, L, ML. Then we're left with the last one, which is MS. So that's going to be equal to plus or minus a half. Okay, so say we have these 2 electrons here. We have the quantum numbers for these are going to be the same more or less up until the S value. So N is equal to 2, L is equal to 1, ML is equal to -1. And then for, let's see, let's change the color. So for the red electron, MS is going to be equal to +1/2. And then for the other electron, which will be green, ms is going to be equal to, so that's the one pointing down, is equal to the one minus a half. Right. So they have their first three quantum numbers are the same. N, L, and ml values are the same for both of these electrons, but then the ms values, plus a half and minus a half, are different. So the red one here, the one that's pointing up, that's plus a half, and the one that's pointing down is ms, that's minus a half. So up is positive, down is negative. And so that's how we get different sets of quantum numbers. That's why, for example, we can't have two electrons pointing in the same direction. We can't have up and up, because then the ms values would be the same. And that's not allowed due to the Pauli exclusion principle. Yeah, but we'll learn more about that at the start of chapter 7. So, so each orbital can accommodate no more. So each orbital can accommodate no more than 2 electrons. Since each electron is unique, we need a way to distinguish the individual electrons in an orbital from one another, and that's done by the 4th quantum number, which is ms. And so I've just done out a sort of an example of how the orbital filling goes and how the quantum numbers can be assigned there. We'll talk more about orbital filling in chapter 7. So this idea of electrons spin was confirmed using this experiment, the Stern-Gerlach experiment. And so this was done before actually all of this theory was kind of finalized. So 1922 was when it happened, so it was quite a long time ago, almost 100 years ago. If atoms with a single unpaired electron are placed in a magnetic field, they showed there are 2 orientations for the atoms. The electron spin was aligned with the field or opposed to the field. So what is an unpaired electron? So in the previous slide we had, that's not a great color. Let's change the color, go back to red. So in the previous slide we had orbitals, we drew them out as these little lines. So the 3 p-orbitals. So an unpaired electron is one that's on its own. So this is a paired, these are paired electrons here. This is unpaired, so unpaired. So whenever there's an intrinsic property of an unpaired electron, which gives it some ability to align with a magnetic field, and that also contributes to its magnetism and whether or not it's magnetic. So whenever they're paired, they kind of cancel each other out, because one is pointing in one direction, the other is pointing in the other direction, kind of get a 0. But we'll talk about that later. If atoms with a single unpaired electron are placed in a magnetic field, they showed that there are 2 orientations for the atom, either aligned with the field or opposed to the field. So that told that there were 2 orientations. So this electron spin then, since there are 2 pathways in the Stern-Gerlach experiment, there must be 2 spins affected by the magnetic field, one spinning to the right and one spinning to the left. There are multiple ways of talking about this. So there's pointing up, and there's spin down. There is alpha, there is beta, and then there's of course the spin quantum numbers. So generally spin up is plus a half and spin down is minus a half. Spin up is also called alpha, spin down is also called beta, because remember the spin is kind of just a thing that comes out in the mathematics of the Schrodinger equation. So each spin state is assigned a quantum number. ms is equal to plus or minus a half, plus a half for spin up, minus a half for spin down. So here you can see the poles of the electron, so either they're pointing up or they're pointing down. So the experiment results indicate that electron has an intrinsic property referred to as spin. 2 spin directions are given by ms, where ms is equal to plus a half or minus a half. So it depends on the orientation. So you see, like a magnet typically has two poles. It has a north pole and a south pole, an N or an S. And so depending on whether or not the electron's orientation is with the magnetic field or against the magnetic field, we have different orientations. And so it's not that the electrons are actually spinning on an axis, rather it is the mathematics that describe the electrons make it look like they are spinning on the axis. So this is what I was saying. So a lot of this, the terminology at least, that describes the observable phenomena is based on the mathematics. And so it's the mathematics which drives the terminology that we use. So this idea of spin, it's not that they're necessarily spinning in a particular direction, rather it's the mathematics part of it. But we still refer to it as spin. And that's the most common way of referring to it. So the ms is the electron spin. So ms is a spin quantum number and indicates spin. So ms is equal to plus a half, ms is equal to minus a half. We're going over this and over this because it's really important that at least for this quantum number, you realize that there can only be two values. And that's because we have in an orbital, we can only have a maximum of two electrons. One is ms plus a half and one is ms minus a half. Magnetic properties of atoms and ions. So paired electrons are diamagnetic. Ferromagnetic materials are metals with magnetic properties. So if like a magnet sticks to a piece of metal, it's generally going to be ferromagnetic. And then unpaired electrons means paramagnetic. So paired electrons again, it's like something like this. And then unpaired, something like this. By convention, we always, if it's unpaired, we usually just write it spin up. But technically, like this is also okay. But convention says that this is what we do. So paramagnetic is attracted by a magnetic field. Attraction is proportional to the number of unpaired electrons. So more unpaired electrons means a stronger attraction to the magnetic field. Diamagnetic substances are not attracted to a magnetic field. Paramagnetic substances are attracted to a magnetic field. Substances with unpaired electrons are paramagnetic.